which seems to at least be deciding to connect with the tablet, which is a good thing. So we're going to finish off with the last bit of kind of consequences of intermolecular forces. Alrighty, so sorry about that. I'm not sure why, everything decided to go to hell all at once, but it's okay. We'll finish this off. So, again, the kind of like core lesson here for us to understand is that when molecules are attracted to each other, we kind of have two things, right? Of course, they want to be together. They need energy to separate. So it's kind of the two things we're working with here. So we kind of saw this with regard to like the fact that we have to put in heat, melt things or to boil things. These things are like, especially water, very much likes itself. So the water molecules want to be together in either a solid or liquid form. But if we want them to turn into a gas, we have to give them quite a bit of energy. Enough energy to break these IMFs, the intermolecular forces between them, which will allow them to kind of spread out as a gas. So that's one kind of aspect of it. We have a couple others. We have something called surface tension. So if you imagine, here is our lovely water. And I'm just going to draw little water molecules in here. So remember that all these water molecules are, very much attracted to each other. And so we're going to see that because of this, a particular water molecule, let me just keep drawing them because we need more, right? How about another one over here and one more? That's good enough. Okay. Let's take a look at this water molecule, the one that I am drawing in light blue-ish. If we can imagine, that water molecule is, it's interacting with all the other molecules around it. So we can kind of see, there's some attraction there and there, maybe even a little bit there. We kind of have all these like minor interactions going on. Those would be hydrogen bonds, right? So, that water molecule is kind of seeing all the other molecules around it. And so it's kind of a little bit being kind of like attracted in all these different directions. So it's like, hey, molecule up there to my top left, like I want to be with you. Oh, but look, molecule to my bottom left, I want to be with you too. And the one on the right, I want that one. And so it's kind of, it's attracted to all the water molecules kind of around it in a circular manner. However, this one water molecule up here at the very top, let me just redraw that right up here. Of course, there's going to be some other molecules it's going to be attracted to. This water molecule, as we can see, if it's at the surface, it only has other water molecules below it. There's nothing on top of it, right? There's no water molecule. That's air on the top. So there's no other water molecules around it. And so as a result, that water molecule, let's make it purple. The purple molecule does not have anyone pulling on or attracting it on the top. So it, as a result, is kind of pulled down a little bit. It's kind of like the idea of polarity, right? We kind of have this symmetrical thing around the blue water molecule, and so it's kind of being pulled in all directions by all the other water molecules. If we look at the purple one, there's nothing on top, so it's kind of being pulled down towards the bottom. And so as a result, it experiences a force called surface tension. And so that's, surface molecules. How can I fix the spelling of this? No way. Okay. Surface molecules feel a they have a downward attraction. So whereas the blue molecule is attracted in all different directions, the purple molecule at the surface feels a downward pull. And as a result of this, water molecules will tend to form little beads like this if you put them on a surface. So if you try dropping a bunch of water molecules onto a penny, for example, you're going to see you can kind of create this like kind of dome idea. Because the water molecules are being pulled down towards each other, that's strong enough to overcome gravity to an extent. Of course, the more water molecules we put up there, the chances are you're going to spill them everywhere. But you're able to form these kind of little beads like that. And that is a phenomenon called surface tension. So you also know this because raindrops, right, are actually, or if you take a hose or whatever, the water will kind of split into little spheres. Same as rain, right? We see rain as kind of this drop shape, right? But really, they're actually just spheres. And it's actually just the air resistance that's pushing that kind of tail back there. But, water tends to form small spheres as a result of this surface tension. So if you have a particular like brand new shiny surface or freshly cleaned window or something, your water molecule will form these little beads on it because of this surface tension idea. So the net idea here is that you're going to form these kind of little spheres where the molecules are attracted to each other. And so this is going to be a result of intermolecular forces. And we're going to see that any one of these properties we talk about today, the stronger your IMFs are, the stronger those properties are as well. So water has hydrogen bonding, and so it has a high surface tension. And so that's really all. Again, the takeaway here: water molecules are attracted to other water molecules. They tend to form spheres as a result of this. And if you put them on a surface, they're going to kind of form these little dome shapes. Another thing that you might be interested to try is if you can actually float a paper clip on water. You can, maybe just take a glass of water and put a paper clip in there very gently onto the surface of the water. And because the water molecules are so attracted to each other, that paper clip will not sink unless you mess with the surface. So this is also how those little bugs can walk across water, is because of the surface tension. So these are just kind of, more reality aspects of intermolecular forces. Okay, how about another one? So that's surface tension. Viscosity is another one, and that's formally defined as resistance to flowing. What this means, let's give you some examples. Honey is a great example of something that is super viscous. When it's not viscous would be like gasoline. Gasoline flows very easily. Honey, as we know, takes forever. If you try and pour your honey out of the jar, it's going to take its time sliding out. Again, the idea here is that honey has a lot of intermolecular forces going on. Honey is made typically of, sugars and water. And so we're going to see that because those sugar molecules are attracted to the water, they actually kind of slow things down a little bit. So as you try to pour your honey from one container to another, the molecules are all kind of like, hey, I like these other molecules. I don't want to go with the rest of you. And so as a result, it's going to pour very slowly. And we're going to see that the gasoline would be kind of the opposite of that. So, and so really that just means it pours slowly. And we've all experienced that, right? Honey or syrups or whatever tend to be pretty viscous. Whereas things that have low intermolecular forces like gasoline are not viscous. So they flow very easily. So you go to your pump, you're actually pumping pretty quickly. Have multiple gallons per minute there. So it's the opposite of that. And so again here, the stronger IMFs typically result in higher viscosity. If we think about oil versus gasoline, they're both hydrocarbons. But oil is more viscous, right? It flows more slowly than gasoline does. The reason for that is because oil often is much bigger molecules. So gasoline might be something like one of these molecules, heptane. Whereas oils would be something like, something like that. If we can think about it, bigger molecule means more electrons, which means stronger London forces. And the stronger your intermolecular forces are, that means this is going to be more viscous. Okay, and then this is just the opposite. Okay, so this kind of trend can extend to other molecules as well. So similar thing, they're both hydrocarbons, but the more atoms you have in your molecules, the more electrons you have. Remember that London forces are all about random shifts of electrons. And so as a result, your oil is going to become viscous. Alrighty, what else do we have? Oops. We have a property called cohesion. If we put our water into a glass cylinder, we get this shape, which we learned was called a meniscus, right? And we would always measure our cylinder from the bottom. The water is attracted to glass. Glass is polar, by the way, just so we know. So at least the surface of glass is polar. And so we're going to see that because glass is polar, water is attracted to it. And so it can kind of defy gravity a little bit. And kind of climbs up the wall. We're going to see this is kind of a similar idea to capillary force, which is something you'll see in biology a lot more. Is how plants absorb water and can be all rigid and get water from their roots all the way up to their branches. In order to defy that gravity, you have to have these intermolecular forces. So because water loves itself and particularly likes the xylem, I think it's called, of trees, it'll easily kind of say, okay, screw you, gravity, I'm going to go up against you, and no problem. So the reason you see this meniscus of water in a graduated cylinder or something is because of cohesion. I do not have any glasses of water next to me right now, but you could probably even see that in a normal glass of water. You'll see kind of the edges just kind of flick up a little bit towards the glass, just because the water is attracted to it. Okay. I think that's enough of other consequences. It is the xylem. Okay, cool. It's been a long time since I've done plant biology, so... Alrighty. Solids are pretty boring. Phloem exactly is another one, right? The solids we're going to see are pretty boring because they're pretty stable. They don't have a lot of exciting things, but we can kind of talk about different categories of solids. We're going to see we have ionic ones, we have molecular ones, and we have metallic solids as well. So we're going to see that we have kind of different flavors of solids, and they kind of just look a little bit different, and they have slightly different properties, but that's kind of it. So, cool. Let's talk about ionic solids. So we'll do those first. Those would be something like repeating where they have just repeating plus and minus units. So here's our sodium chloride. Make all these minuses, and we'll make these guys pluses. So ionic solids look like this. We never really see just one Na and one Cl minus. In reality, we have a formal term called cajillions. In a crystal. So if you take a look at a salt crystal, you can see a crystal of salt with your eyes, right? Where we can definitely not see atoms with our eyes. And so it's actually something we never see just one pair of sodium and chloride together. We actually see cajillions of them arranged in these kind of repeating patterns where we have positive, negative, positive, negative, positive, negative. And so, yeah, cajillions is a real word. I don't have a good number for you, so yeah, cajillions. Okay, and so you kind of see these together like this. Ionic solids typically have high melting point. I guess I should write that out. That's the temperature at which they melt, of course. Many of these dissolve in water. And conduct electricity. And most are pretty brittle. So if you take your salt crystal and smash it with a hammer, it's just going to break apart. You'll make it very powdery. So you can think you have all these different forms of salt. You've got kind of like rock salt. You have, like kosher salt crystals. You've got table salt. You have popcorn salt. Those are all just different sizes of crystals, but it's the same compound. So if you smash your rock salt to bits, you'll make it into little small crystals, but they'll still be sodium chloride crystals. Okay, pretty boring. Let's talk about covalent solids. So these ones are just like massive networks of covalent bonds. So something like diamond, just looks like you have this kind of repeating, just carbons connected to each other. And so again, you're going to have, many, many atoms connected covalently. And so that's just kind of what they look like. These things are typically not soluble. In water. Very exciting stuff. Some of them are, some of them aren't. It just depends on what the solid is going to be, if it's polar or not, basically. So something like a diamond like this, where we just have all these carbons connected to each other. The whole thing is going to be non-polar, just all carbons. But something like a protein where you have tons of these different molecules connected to each other covalently. Many proteins are soluble in water. Some are not, but most are, right? So, you can have different kind of other ways of talking about them. These are also pretty brittle. It's just the way that they are. Again, you take your hammer and smash your diamond. You could do it. Probably not a smart idea, but you could. You could do it with graphite. You could do it with sugar crystals. These would all be the same idea, where you just have these kind of covalent networks. Alrighty. So these can be crystalline or amorphous. I believe we talked about crystalline and amorphous solids early in the semester. We'll just remember that crystalline ones are like orderly, and amorphous ones are kind of chaotic. So, a nice network solid things are nicely connected together. Where a chaotic one, this is like kind of crazy, but things are not organized as much. Here, I'll make this one really organized. There we go. Where we have amorphous ones which are kind of just chaotic. So crystalline solids are nice and orderly. Amorphous ones are chaotic. So this would be something like glass is an amorphous solid. Chaotic, we can see through it very nicely. Crystalline ones we typically can't see through as nicely. This would be like many... this would be like some of those polymers or plastics. Like Kevlar, for example, would be a crystalline solid. Those tend to form more orderly ones, whereas you could definitely have polymers that are amorphous, but a lot of them will be crystalline as well. So it just depends on what your particular polymer is. Alrighty. Cool. The last solid we have is a metallic solid. So metallic solids are pretty interesting. They it turns out that the electrons within metals can kind of just hop off and go to other metals nearby. They are, as we remember, metals typically have like kind of loosely held valence electrons, especially the ones in the d orbitals. And as a result, metals are sometimes described of a sea of electrons. So the metals that kind of just like lose their electrons are all going to be positively charged a little bit. And the electrons are just going to be hopping around between different positively charged metals, metal atoms. And so they just kind of hop around, and it's kind of just an ocean of electrons that just move continuously between different atoms. And so that's why metals tend to be solids as well, is because of this property, because their electrons are kind of loosely held, so they can just hop over to other nearby atoms. As a result, these conduct electricity. Electricity is just electrons, right? So these already have electrons just hopping around, flowing, ready to go. So if you go ahead and kind of force it to carry electrons, it says, no problem, I got this. These ones are squishy, is going to be our layman's term, but we would call it malleable in formal terms. That means we can kind of flatten them out really easily. If we strike a metal with a hammer, it's just going to kind of deform itself. It'll like flatten out instead of shattering. So these are typically strong, right? These have kind of medium melting points. I think I forgot to mention that these could, depending on the network solids, here we are, I'll just say various melting points. So some, like diamond, have pretty high melting points. Others, like plastics or glass, have relatively low melting points. Okay, and metallic solids are going to be kind of in the middle. So we know some metals melt really easily. Some metals take a lot of temperature to melt. So it's just the way that those are. Cool. Hooray! We're done with solids. Do we have any questions about these? Oh, by the way, metals don't dissolve in water. And we already know that, right? Your pots and pans are made of metal. And thankfully, when you're boiling your pasta, the pans don't dissolve. That would be pretty awful, right? We would have to have something else. We'd have to cook our food in diamonds instead. Be very rich like that. Okay, so there we go. Yeah, MP is melting point. Yeah. Alrighty. Hooray, we're done with solids. And liquids, I guess. Do we have any questions on those? While you type out your questions, I'm going to plug in my laptop because I'm not sure it will survive streaming for so long. So, oh, goodness gracious. Did I forget the charger? That would not be good. Any questions? Next, we're going to talk about gases. So now that we've talked about liquids and solids and all these, here it is, intermolecular forces, we're going to talk about gases. Because gases are going to be actually quite different from the other ones that we've talked about. So solids and liquids are pretty similar. They have, good intermolecular forces. We're going to see the opposite for gases. Okay, laptop is plugged in. They don't. That's what we're going to see. Okay, I'm going to just go ahead and save this file separately, just so it's easy for you guys to find, so you don't have to worry where the heck did we start gases. So let me just go ahead and put that up here for you guys. That's this one. Okay, and we'll start a new one for gases. This is going to be chapter 7 in our textbook. And I think it's either 11 or 12 intro, I don't remember. But you'll see it. It'll be called gases or gas laws or something. So, there we go. So, we're going to see that the primary characteristic is they do not interact. So they will have no intermolecular forces. This is kind of one assumption we make. There may be some small minor interactions that gases would undergo, maybe like a quick London force here and there, but by and large, they don't interact with each other. We can think of gases, they're things that are really far apart. And they're just too far apart to interact with each other. So, very far apart. And so they don't interact. So this chapter, actually we're going to have a bit of math with this one. This is a pretty math-heavy chapter. But the math that we do, it's just, honestly, there's really one formula that you would need, and that's it. So it is a magic formula. Okay. We can think of gases kind of as, like billiard balls is a pretty common comparison. So if you imagine like a pool table and you have all these balls just like moving around each other, most often they just kind of slide past, or they're going past each other doing their own thing. Typically we imagine gases they move in straight lines. It's typically something we see. So they just kind of go until they run into something. And that could be a wall, that could be other gas molecules. It could be some container, a balloon, whatever, or, our eyeballs, whatever. Gas molecules just move around in straight lines, roughly. And they move their speed is proportional to their temperature, right? So temperature is technically a measure of kinetic energy, but for gases, that's going to be pretty much just speed. So a higher temperature means faster molecules. And that makes sense, right? The more energy they have, the faster they're going to be moving. I typically, for this chapter, I'm going to kind of call everything a molecule. Well, sometimes it's actually just atoms. Like helium would just be an atom, but just for consistency and not having to worry about it, I call everything a molecule when we talk about gases. Even though that may not be like technically the most correct way to do it. It's just easiest. It doesn't really matter. Atoms and molecules behave exactly the same when they're gases. So. Alrighty, so we kind of have one more thing that we think about with gases, is that when gases collide, all the energy is conserved. That's kind of the weirdest one. This is more of a physics thing, I suppose. But if gas molecules collide together, they don't lose energy as heat. That's what we're saying. So when they collide together, they just bounce off each other, and off they go. So they don't produce heat when they collide. This is probably something that's not quite true, but it is an assumption that we need in order to make our calculations work. We all know that if we collide our hands together, they'll produce heat, right? You can feel the heat of the friction. We're going to assume that when gases collide with each other, they don't have any friction. So it's just an assumption we make. Alrighty. So with gases, we often talk about them in terms of four different kind of quantities. And for this one, we might also describe these as properties. One of them we've already mentioned, right? We have temperature. That is going to be one thing we can talk about with gases. Because we see that temperature and the speed of the gases are proportional, they're correlated with each other, that this is one thing we're going to want to look at when we're talking about our gases. So temperature is going to be how fast they move. We could also talk about the amount of gas particles, and that's just how many there are. So in your container of gas, how many gas atoms or molecules do you have in there? That's the amount that we see. We also have the volume. Since we know gases will always fill their container, this is how much space they take up. So, if you have a gas tanks of different sizes, those will just have different volumes. And so we're going to see that that's another property we're going to look at here. And the last one, arguably the most important one, and perhaps the one that we are least familiar with, is pressure. And pressure is how often the gas molecules collide with walls. So those could be walls of a container. They could just be objects somewhere. I'll just write or objects. Yeah, that'll be easier. So believe it or not, we are being bombarded with gas particles all the time. Oxygen, nitrogen in the air, these are gases that are just flipping around, moving in straight lines. They collide with us all the time. And so we're experiencing a pressure called atmospheric pressure that we have kind of always on us. So our bodies are built for that. We are used to having this pressure on us. So if we go out into space or something, you've probably seen in cartoons that because there's no gas in space, it's a vacuum, there's no pressure. And because there's no pressure, like in cartoons, you swell up and explode, like that. It's not really how it works. You'd probably just freeze and become a solid. So we're not gases, so we would not expand so easily. But you'll see in the textbook and maybe online, like if you put a balloon or something, or a marshmallow or some brie or whatever, some cheese into a vacuum chamber and get rid of the gas, get rid of that pressure, these things will often expand quite a bit. So again, that's kind of your cartoony, look. The astronaut took off his helmet and now he's exploded. So, or whatever. So, silliness. Okay, so we can talk about units of all these things. Technically, by the way, for physics, pressure is equal to the force over an area. So, you will probably have seen units like PSI, which is pounds per square inch. Pounds is a force. Square inch is an area. These are common units. For the metric system, we have pascals. In chemistry, we have a few other ones that we talk about. We talk about ones called atmospheres, which is abbreviated ATM. We talk about bars, which are very similar to ATM. And then we also have millimeters of mercury. Especially for those of you going into healthcare, you'll see the millimeters of mercury unit all the time. That's one that you use a sphygmomanometer to measure blood pressure with. It comes out in units of millimeters of mercury. You'll also see torr. There's a lot of units. And so we have a few things to talk about with these. PSI we're pretty much not going to use because it's a US unit. We don't really use US units in chemistry. We use metric ones. So 1 atmosphere is the pressure at sea level. Let's just say sea level. So that's all the pressure of the atmosphere pushing down on some object at sea level. And that's what 1 atmosphere is. That's kind of where we get that unit. So it's an entire atmosphere. We're going to see that this is going to be equal to $760. I just wrote 1. 1 atmosphere is equal to 760 millimeters of mercury, to a pretty good number of sig figs. We also have a unit called torr, which is a more exact millimeter of mercury. For us, in light blue, millimeters of mercury and torr are the same. We are going to say they are exactly the same. We're not going to worry about this very slight difference. The only difference is sig figs way down the line. So chances are your other measurements are going to determine your sig figs anyway, so let's just not have to worry about that. Okay, so for us, they are the same thing. Okay, these are typically the units that we are going to use in this class. However, a bar is actually a pretty common unit now. So this is a more formal unit. A bar is 10 to the 5th pascals. You will not need to memorize these. I mean, well, this one you'll probably want to memorize. But again, like, it's online. I have no way of stopping you. This one you'll want to memorize, the 760. But these ones you don't have to worry about. We're going to work mostly with atmospheres and millimeters of mercury or torr. So we're not going to work with bars as much or with pascals. But those would technically be the conversions between them. Alrighty, I want to start talking about this now. I don't, but let's just cover the units of our other quantities, and then we'll start relating them to each other. So for temperature, right, you know, we kind of have two choices. We could either use degrees Celsius or Kelvin. For gas laws, we must use Kelvin. Everything works with Kelvin for the gas laws. We're going to see that for degrees Celsius, it does not work. And we're going to see that tomorrow. Examples of why degrees Celsius will not work for our gas laws. And so we're always going to use Kelvin. So just so we remember, Kelvin is degrees Celsius plus 273.15. Okay, so we're always going to use Kelvin for our unit of temperature when we're dealing with gases. When we did the MCAT stuff yesterday, we could use Celsius or Kelvin. That one's okay. For gases, we must use Kelvin. Have to do it. Okay. Easy enough. Okay, so we've seen volume before as kind of a measurement. Typical volume units would be meters cubed or liters, or various derivations thereof. Remember that 1 meter cubed is 1,000 liters, or a cubic centimeter is 1 milliliter. These tell the same thing. These would just be, again, common units that we would see in gases. Alrighty, and the last one, what is that? Quantity, okay. We use everybody's favorite unit, the mole. So, right now in our toolkit, we know how to go from grams to moles, right? We know how to do this because this conversion factor is called molar mass, right? So we're going to be using moles all the time in this chapter. So you may want to review going from grams to moles using molar mass. Or backwards. You can go moles to grams as well. So those are going to be kind of the quantities we're going to be talking about in this chapter, as well as units associated with them. Alrighty, so I guess we're gonna end a little bit early today, so I guess it's not a bad thing that we had all those snafus at the start. Um, but tomorrow we're gonna be able to relate all of these to each other, and we're gonna come up with some fun formulas as a result of it. Alrighty, so with that, I'll see you all tomorrow. I guess I'll put up some homework for your intermolecular forces so you can start working on that. So I'll probably do that later today. And yeah, and then tomorrow we'll continue our exploration of gases. Okie doke. I will see you then.